And welcome back. As we continue our cosmic journey, we are now going to shift into looking at what happens when gravity moves to the extreme. And in order to do that, we need to first introduce some basic ideas about general relativity. So the most common thing people start thinking about when gravity runs away is, of course, the black hole. Most stars will typically end their lives as white dwarfs or as neutron stars. However, when we get a very massive star that collapses near the end of its life, not even the mutual repulsion between densely packed neutrons can support the core against its own weight. If the remaining mass of the star's core is more than about 3 times the mass of that of our sun, gravity will simply overwhelm any other force and simply will crush that core until it occupies an infinitely small volume. A star, of course, in which this occurs may become one of the strangest objects ever, that of a black hole. So to really truly understand what a black hole is and how it really kind of can influence its surrounding, we first need a theory that can really describe the action of gravity under such extreme circumstances. And to date, our best theory of gravity is the general theory of relativity, which was put forth in 1916 by none other than Albert Einstein. Now, although the detailed calculations of general relativity do involve a great deal of higher mathematics, the basic ideas are not difficult to understand, and that's all we're going to need to be able to dive into how black holes are functioning. Moreover, general relativity is a very important property here because it helps explain how matter interacts with other matter inside of space and time. In order for us to really first explain this in some simple terms, let's look at the principle of equivalence. And to demonstrate this, we're going to use an elevator example. And there's 4 different states in an elevator that you can have. The first is the elevator is at rest. You simply would feel your normal weight as you're standing within the elevator. If the elevator were to accelerate as it descends, you would actually feel lighter than normal. You probably feel this when the elevator starts going real fast. You feel like all of a sudden a brief period of lighter weight. If the elevator then accelerates though as it descends, you naturally would feel heavier. You feel this brief period of where all of a sudden everything weighs just a little bit more. And if the cable were all of a sudden cut and the elevator were to start to free fall down into the abyss, well, you would experience a brief period of weightlessness. And so let's take this back to our general theory of relativity. What Einstein postulated is that there's no experiment that we can perform inside a sealed laboratory to determine whether someone is floating in space or whether they're falling freely in an elevator. As far as the individual is concerned, in that given moment, the 2 situations are completely equivalent. So this idea that free fall is indistinguishable from and hence equivalent to zero gravity is what we call the equivalence principle. And so let's look at this with another example to really kind of ask the question of, is something gravity or is it acceleration? And so here we have 2 people playing catch as they descend into a bottomless abyss. Now, since the people and the ball are falling at the same speed, it would appear to these 2 individuals that they can play catch by simply throwing the ball in a straight line between them. So the person on the left passes to the person on the right, the person on the right passes to the person on the left, and so on and so forth. Now, within their individual frame of reference, there appears to be no gravity because, again, they're just passing it back and forth in a straight line. However, if we look at this image here, we can see as they are falling, that ball is not falling in a straight line, but is actually curving as it moves from one individual to the next. And so let's look at this now with another example. Let's say you're an astronaut in the International Space Station. And of course, that is a space station that's orbiting Earth in an environment that is actually very similar to that of a free-falling box. And while in free fall, the astronauts live in kind of a strange world where there seems to be almost no gravitational force. For example, one can give a wrench a shove and it will just move at a constant speed across the orbiting laboratory. A pencil that you set in midair will remain there as if there's no force acting on it. It won't fall, it won't rise, it won't do anything, just stay wherever you left it. But these appearances of how these different objects are moving is kind of misleading. There is a force in this situation as both the ISS and the astronauts are continually following around the Earth. In this case, they're being pulled by the force of gravity. But since all things fall together inside the ISS, all the gravitational forces appear to be absent. Thus, the orbiting ISS gives us actually a very excellent example of the principle of equivalence, or how the local effects in a little scenario here, so in our box, which is the ISS, of gravity, can actually be completely compensated for by the right acceleration. To the astronauts, falling around the Earth creates the same effects as being far off in space, remote from all gravitational influences. And so let's use this idea now to really talk about the paths of light and of matter. Because Einstein postulated that the equivalence principle is a fundamental fact of nature, and that there is no experiment inside any spacecraft by which an astronaut can ever distinguish between being weightless in a remote space or being in free fall around a planet like Earth. And this would, of course, apply then to experiments with beams of light as well. But the minute that we start using light in our experiments, we are led to some conclusions that can actually lead us to general relativity and give us a new view of how gravity functions. It appears to us in everyday observations that beams of light travel in a straight line. For example, if you've ever taken a flashlight or a laser pointer and you point it at the far wall, it looks like it has moved in a straight line. Now, let's just imagine for a moment that a spaceship is moving through empty space, far from any gravity. So you're not near any stars, near planets, you're just out in the void. So let's send a laser beam from the back of the ship to the front, and it's going to travel in a nice straight line and will land on the front wall exactly opposite from the point which it left the rear wall. I mean, not much different than how we would expect that to behave. Now, if the equivalence principle really applies universally, then the same experiment performed in free fall around Earth should give us the same result. So let's go ahead and have a hypothetical spaceship here, and let's have it moving to the left in its orbit about a planet. It could be Earth, could be another one, but let's just go ahead and have light beam from the rear A toward the front B. Meanwhile, the ship is falling out of its straight path. It's of course orbiting the planet. We might expect the light to strike at point B prime. This is, of course, above the target of the ship, because if it is truly traveling in a straight line, it should continue on from the path of which it was going. However, instead, the light is going to actually take a curved path and strike at C, which, of course, inside the spaceship just simply means I am at the back of the spaceship, and now I'm shining that light, and now it's hitting the front of the spaceship. For the principle of equivalence to be correct, gravity must be able to curve the path of a light beam just as it curves the path of the spaceship, because if it didn't, that light would be hitting a different point. So in this case, when we look at the light, much like the ball that we saw earlier that was thrown back and forth in that abyss, the light has to fall with the ship as it is moving in the orbit around the planet. But a question you might wonder is, why or how does light curve when it doesn't have mass like that of a ball? So Einstein actually came up with a solution for this. He suggested that the light curves downward to meet the front of the shuttle because, well, Earth's gravity is actually bending the fabric of space and time. This was a pretty cool radical idea, but it did us some favors in keeping the behavior of light the same in what we would consider both empty space and also in a free fall scenario. But it does change some of our most basic ideas about space and time. Those ideas, of course, are going to be very fundamental as we move forward to really examine what a black hole truly is.